me introduce the first talk that I'm pretty, okay. So I'm pretty sure that you heard about this work because it won an award yesterday. So the first presenter is Young Soo Kim, who is a second-year PhD student at KAIST, working with Professor Zhang Park. His current research focuses on three main areas: adaptive AI, on-device acceleration for autonomous system, and the third one is low-precision quantization for ML applications. So whenever you're ready.
All right. Okay. Hello, everyone. My name is Yoon Kim, and I'm a PhD student at KAIST. And today I'm going to introduce our paper, the DaCapo, the acceleration solution for continuous learning in autonomous system. On-device AI is rapidly approaching, introducing a new wave of local intelligence. This technology is widely applied to the applications of autonomous systems, including robotics, autonomous vehicles, and UAV systems, where immediate data processing is important. And also, many big tech companies are moving toward the on-device AI. They are actively developing their specialized AI chips and services. When we deploy on-device AI to real-world applications, we have to consider features of deployed environment and DNN models to deploy. About the environment, there are constant changes in data distribution, which are known as data drift. These changes make it difficult for DNN models to guarantee high accuracy. And in terms of the model, on-device AI have generally lightweight models because the system has limited computing power. Consequently, the on-device DNNs are particularly sensitive to the data drift because they have a limited model capacity, making it difficult to maintain their accuracy. And truly, the data drift has a significant impact to lightweight model. The following figure shows the accuracy over time of the CNN model on actual dataset. According to this figure, we can see that accuracy is decreased from the point of the data drift. To solve this problem, the system requires retraining the model over time also for the adaptation to the changing environment. And one of the primary solutions for this runtime adaptation is continuous learning. This approach constantly retrains the model with the new data, and it has been recently explored in both systems and architecture field. This retraining process maintains the model accuracy in good quality by adapting to the latest information from the current environment. And let's take a look at how this continuous learning works at the system level by breaking down the entire process. The first, there's an inference job in the system which handles the responding to the request. To retrain this model, the system requires two additional steps. The first step is labeling. For this job, a large DNN is used to generate high-quality labels. Of course, the labeling model is too large, so we cannot use this model for every single frame. After obtaining this data, the system constructs the training dataset and executes the retraining process and update the recent model for the next inference. In summary, the continuous learning system requires these three DNN kernels. In prior approaches, edge devices offload the model adaptation kernels to the GPU system via network connection. However, operating the continuous learning with this cloud server has some limitations. The system might have private data that cannot be sent to the server, or network connection is not always guaranteed, and latency itself can be a concern. Therefore, we aim to build an on-device continuous learning system. However, designing on-device system for continuous learning have new challenges for it. The first challenge is designing a way to share the on-device resource. The system must consider that the main three kernels require different computational demands. The next challenge is scheduling the retraining and labeling jobs. Because how efficiently the system retrain the model and label the data gonna directly affect to the accuracy improvement. And lastly, within the constraint of the limited resource, the system must leverage the hardware to provide sufficient and efficient performance for the system. To explore how DaCapo system addresses these challenges, let's get into looking at the first challenge. When executing the continuous learning kernels, one of the simple solutions we can apply is just time sharing across the kernels. However, this naive approach has a problem, the resource inefficiency. To solve these challenges, the DaCapo system applies a vertically partitionable systolic array. This architecture can be divided into two sub-systolic arrays, and to achieve this, there are two pairs of the weight and output buffers at the top and the bottom of the systolic array. And each processing element has bidirectional bus to communicate with vertical neighbors for data transmission. By using this architecture, the system allocates a small size accelerator for the inference at the bottom, providing just enough resource for satisfying the latency requirement for inference. Additionally, the other jobs, the retraining and labeling, can utilize the remaining computing powers at the top accelerator to execute the model adaptation process. And the next challenge is resource scheduling. And even after allocating spatial resource to the kernels, the system still needs to schedule the retraining and labeling jobs. It is because how these kernels are scheduled affect to the accuracy improvement after the model adaptation. To solve this, the DaCapo system allocates shorter times for retraining and labeling. With this approach, the system can update the model more frequently, and at the same time, the system constantly monitors the changes of the accuracy. These changes are used to detect the data drift. The system continuously calculates the loss in accuracy between the model adaptation intervals, and if the accuracy loss is quite significant, then the system recognizes this situation as data drift and allocate additional time for labeling. This method allows the system to quickly detect the data drift and provide enough new data for rapid adaptation. And the next challenge is resource constraint of the on-device system. The limited computing power makes the system difficult to show optimal performance when operating the continuous learning. And this inefficiency also reduces the adaptability for the data drift. So this implies that we need to design more performance and effective continuous learning system which can leverage the on-device computing power. To achieve this, the DaCapo system applies a quantization technique to improve the performance and efficiency by making the previous two solutions more feasible. To quantize the models, we apply the block floating point format. Specifically, we choose to use the Microsoft MX, which is a recent variant of the BFP format. We don't just use the existing solution, and we also enable the flexibility to choose the best precision for the DNN kernel to operate the continuous learning system. For retraining, we set a higher precision, the MX9, and for other two tasks, the labeling and inference, we set a lower precision. It is called MX6. It maintains the model accuracy while improving the system performance. To support this dynamic precision on the systolic array, we design reconfigurable processing elements. When we look at the single processing elements, it consists of the hierarchical MAC unit that start with the 2-bit multipliers. And using multiple bit shifters and multiplexers, the system can construct adder tree that can support up to 8-bit multipliers. By doing so, the system can set bottom accelerator to execute 4-bit precision, and the top accelerator iterate the reconfiguration of retraining and labeling in different precision. And to evaluate DaCapo system, we use a BDD100K, a real-world driving dataset, to construct different scenarios, including data drift. For baseline, we choose two state-of-the-art continuous learning systems, which are called ISCA and UMU. For the comparison with DaCapo, the baselines are operated on the on-device GPU. About the implementation of DaCapo, we built a system simulator based on the ScaleSim, and to verify DaCapo's hardware, we implemented our microarchitecture using Verilog RTL and synthesized it with Design Compiler and Coctai. The first evaluation result is end-to-end accuracy. The horizontal axis shows the combination of inference model and labeling, and the vertical axis shows the averaged inference accuracy for each scenario. And we also report the geometric mean across the entire scenario. And we can see that For all the cases, DaCapo shows optimal accuracy performance compared to the baselines. This is because an efficient resource scheduling and microarchitecture for the flexible precisions allow the system to effectively handle the data drift and process each kernel with suitable precision. Consequently, the DaCapo achieves up to 6.5 and 5.5% higher accuracy than other baseline, the IKEA and UMU respectively. And the next evaluation is accuracy over time, where we can see the trends of the accuracy. The horizontal axis shows the time, and vertical axis shows the inference accuracy. There are colored dots on the lines, which indicate the end time of the retraining. And in this figure, there are two data drift points over time. The first thing we can see is that the baseline struggle with data drift. This is because the baseline system cannot effectively manage the on-device GPU resource, and consequently, they show low accuracy trend. However, DaCapo system recover accuracy from the data drift by effective scheduling. Specifically, when we look at the blue-colored arrow, we can see that the system detects the data drift and allocate additional time to label, ensuring a sufficient amount of the new data for the rapid adaptation. If you refer to our paper, there are other meaningful evaluations such as analysis of scheduling decision, experiment with extreme data drift scenarios, and power area analysis for hardware. And here's the conclusion. We propose DaCapo, an acceleration solution for on-device continuous learning in autonomous system. Our contributions include the vertically partitionable systolic array, designing a scheduling method to handle the data drift, and applying flexible precision to improve system performance. As a result, DaCapo achieves higher accuracy compared to the state-of-the-art continuous learning solutions. And that's it for my presentation, and thank you for listening. If you have any question, I will be happy to answer.
If there are any questions, please go to the mic and introduce yourself. So while we are waiting for the questions, I can ask you a question. So can you also elaborate on the probably applying the techniques that you suggested to other models, multiple models, or like for instance, NLP tasks or LLMs?
Yes, absolutely. The multiple model operation can be a new research direction for on-device continuous learning, because when we think about the autonomous system, there's not always a single model. Even though the single system and for single decision, multiple DNN models can be jointly operated. So, however, the hardware cannot support this multiple operation because there might be an imbalanced workload between the various multiple DNN on the autonomous system. So I think that can be possible.
Awesome, thank you. So if there are no other questions, let's thank the presenter again.
Just talking. What else?
Let me see if this is okay.
I think you are words. So
Perfect.
just present.
All right, so let us go to the next presentation. Our next presenter is Dr. Feng, who is an assistant professor from Shanghai Jiaotong University. He is interested in mobile architecture for AI, algorithm, hardware co-design, and in-sensor computing. So it's all yours.
Thank you. Hello, everyone. My name is Feng. I'm an assistant professor at Shanghai Jiaotong University. Today, I'm going to talk about our work, BlissCam, boosting eye tracking efficiency with learned in-sensor sparse sampling. So this is a joint work with Washington University in St. Louis, University of Rochester and Northeastern University. Now let's get started. Eye tracking is an important application in many fields, such as medical studies, human-machine interactions, AR, VR, etc. However, an always-on eye tracking would consume over 2 watts, which is over 50% of power budget of a typical VR system. A typical eye tracking system would look like this. So first, a near eye camera would capture the eye movements, and the captured information will then be sampled and converted from the analog signal to the digital signal. And then the digital data will be transferred and processed by the backend processor to obtain the gaze information. And this gaze direction will then be used in the downstream task. In this system, ADC consumes over 66% of sensor energy, and it also introduces high data volumes between the front-end sensor and back-end processor. So throughout the history, there are numerous techniques have been proposed to optimize the sampling stage. However, prior works either require high sampling rates or high computation overhead. In this work, we leverage the domain knowledge of eye tracking to achieve fast and efficient pixel sampling. Here we propose our work, BlissCam, which consists of 2 main components: a learned sampling algorithm that drastically reduces the sampling rate, and also a sensor and processor co-design to couple with this algorithm. Now let's talk about our algorithm first. So the key idea is to design a dedicated sampling algorithm that can leverage the domain knowledge. Specifically, our algorithm has an in-sensor sampler that can predict important pixels. And then we only process those important pixels at the backend processor. Most importantly, we backpropagate the loss of this backend task to the learned sampler to refine the sampling strategy. By applying this idea, we propose our dedicated sampling algorithm for eye tracking. So in conventional eye tracking pipeline, a near eye image will be sent to an eye segmentation stage to obtain a segmentation map. And then this segmentation map will be used in the gaze estimation stage to get gaze direction. And our key idea is that we first predict the region of interest in the image, and then only process the region of interest for the rest of the pipeline to reduce the overall computation. And the way to extract ROI is inspired by event camera. Unlike conventional camera, which capture images frame by frame at fixed time frequency, event camera only emit events whenever the light intensity surpasses an error threshold, a threshold. And using this mechanism, we emulate event camera in software. And as we can see, event map laterally encodes some ROI information. And emulating event camera in software is very lightweight. It only requires 2 operations. Now I will introduce our sparse sampling algorithm. So our sparse sampling algorithm will first perform eventification to generate event map. And then this event map will be fed into a ROI prediction network, which is a very lightweight DNN network that can predict the ROI image. And then we just randomly sample pixels within the ROI to reduce the overall data traffic. And for the rest of the pipeline, we only transform the sample pixel to the eye segmentation and gaze prediction to get final gaze direction. Now, if we look at all the operations on the top, we can move those operations inside the sensor. We can drastically reduce the data communication between the sensor and backend processor. And from our experiment, we show that we only need to send roughly 5% of pixels compared to full resolution. In addition, we also propose a VIT-based eye tracking eye segmentation network to enhance the robustness of eye segmentation. So that's our algorithm. Now we'll talk about our sensor and processor co-design. Here we show the sampling algorithm. And a straightforward design is to have a 2D image sensor. Now on this image sensor, we have a 2D pixel array that captures eye movements, and the ADC converts analog signal to digital signal. And then for the rest of the computation, we have some dedicated PEs for eventification, a tiny NPU for ROI prediction, and another dedicated PE for random sampling. Now, this sounds simple, right? However, there's 2 issues with this design. First, as I mentioned earlier, ADC conversions will consume 66% of the sensor energy, And with this design, we cannot resolve this issue. Another issue is that implementing a true random sampler in digital is power hungry. Therefore, we propose our BlissCam sensor design. In our BlissCam sensor design, we adopt a 3D sensor architecture. On the upper layer, we have a pixel array that capture eye movements, and we have a dedicated analog PE to perform identification. At the bottom layer, we have ADC to convert analog signal to digital signal, and we have a tiny MPU to perform ROI prediction. And between these two, we use micro TSV for data communication. And by doing so, we can reduce 83% of pixel readout and 95% of off-sensor traffic. Now let's look into details how we perform identification. Here I just show a conventional sensor design. And this is our design. We basically augment the conventional sensor design by adding 7 transistors. And our experiment shows that our pixel dimension is comparable with state-of-the-art pixel dimension. And by adding these 7 transistors, we are able to perform ROI prediction and also identification. ROI pixel readout and identification. Next, I will talk about how to perform random sampling. So here we use the SRAM cells in ADC. Specifically, we leverage the meta stability of 10-bit SRAM cells during the power-up. So during the power-up, the meta stable state will randomly latch to 1 or 0s due to random noise. And then we will count ones in this 10-bit SRAM and compare with the predefined threshold. So if the total sum is over the threshold, we will select this pixel. Now let's go over the overall architecture design. So we have a 3D sensor. At the upper layer, we have a 2D pixel array and analog compute units. And we also, at the bottom layer, we have an ADC and SRAM and a tiny MPU and a small buffer to store image frame. And between the upper layer and bottom layer, we use micro TSV. In addition to the image sensor, we also design a host MPU that has a 32 by 32 pixel Cicero array with a 2 megabytes on-chip buffer. And to communicate with sensor and backend MPU, we use a standard MIPI CSI interface. Now let's see the evaluation. Here we first show the accuracy comparison. The x-axis shows the compression rate, higher the better, and the y-axis shows the angular error, lower the better. And we also highlight the acceptable error rate for eye tracking. And here we compare against 2 baselines, EDGATE and RTNet. Those are state-of-the-art eye tracking algorithms. And as we can see, as the compression rate goes up, those state-of-the-art algorithms cannot retain the error rate within the acceptable threshold. In comparison, our algorithm can achieve a higher compression rate while maintaining the error threshold within the acceptable error threshold. Next, I will talk about energy savings. Here, the x-axis shows the energy per pixel, and y-axis shows different variants or different baselines. And in our case, we compare against 2 baselines. The first one is MPU full, and in this baseline, we capture the entire image and send the entire image to the backend processor and perform all the computation in the backend processor. And the second variant is signal sensor plus MPU, and this variant perform all the sampling algorithm inside sensor, but in the digital domain, and then send the sampled pixel to the MPU and perform the rest of the computation. Now let's see the results. So as we can see, MPU full introduced significant energy overhead primarily because 4 main components: pixel readout and MIPI interface and SoC's memory and compute. By moving the sampling algorithm inside the sensor, we can drastically reduce the energy for SoC. However, we still introduce some overhead because the sensor memory and also we cannot resolve the sensor pixel readout. And by moving the computation in the analog domain, we can further reduce the energy. We basically further reduce the sensor readout and the sensor memory. In our paper, we also explained our co-design can achieve 1.4 times speed up. Due to time limit, I omit the detail here, but please refer to our papers for more details. So in conclusion, sparse in-sensor sampler is critical to reducing the energy consumption and end-to-end latency of eye tracking. And sampling within an image sensor drastically reduces the amount of data that has to go through the subspatial energy-intensive stages. And lastly, we demonstrate that BlissCam reduces pixel volume by 95% and achieves 8 times energy reductions and 1.4 times speed up. And that will be end of my talk, and I'm happy to answer any questions. Thank you.
Any questions from the audience? Yes, please.
Hi, nice work. This is Sarita Adbe from University of Illinois. So you had a baseline error.
Yes.
So what do you assume as the ground truth error accuracy requirement?
So we have a ground truth, which is the gaze position. And from the studies, they show that if the angular error is within 1 degree, it's tolerable and it's acceptable error rate. Yeah, that's.
Okay. All right. Do you think that by messing around with that ground truth error rate, you can squeeze more efficiency?
Yes. We do see that if we just lower the accuracy a little bit, we can achieve significant efficiency for eye tracking. Yes. Sure.
Okay. All right. Thanks.
Yeah, thanks.
If no more questions, let's thank the speaker again.
This one is allowed.
Yes.
Okay. This one.
All right, so let me introduce our next speaker. Our next speaker is Moon Han, who is currently pursuing a PhD degree in computer architecture at the School of Computer Science and Engineering, Beihang University, Beijing, China. His research interests include computer architecture and deep learning accelerators, and he is seeking a postdoc position to further his research and contribute to advancements in computer architecture. So if you are looking to hire a postdoc, don't miss the opportunity of reaching out to him.
Thank you for the introduction and thank you for attending my presentation. My name is Meng Han from Beihang University, China. I'm excited to present our work at BitNN, a bit serial accelerator for k-nearest neighbor search in point cloud. A point cloud is a collection of points that directly represents 3D sensor objects. Recently, point cloud have been employed in many scenarios, such as autonomous driving, robots, and virtual reality. This application usually employs the 3D sensors, such as LiDAR and scanner, to generate the point cloud. Nowadays, many tasks rely on the efficient processing of the point cloud data. We analyze some typical workload, and the results reveal that the KN search is a key operation in point cloud-based application. It can account for 16% to 18% of total write time. As this application operates within energy-constrained environment and expect to react to the environment, poses challenging on real-time and energy-effective processing. Moreover, with the development of the 3D sensor technology, a frame of the point cloud can be generated within 15 millisecond for 416,000 points. To meet the real-time requirement, the processing latency should be less than 15 milliseconds. However, existing implementation struggle to meet the real-time requirement due to the increasing size of point cloud, highlight the need for more efficient and scalable solution to handle the computation. So let's drive in the KN search. For a given query point, the KN search finds k-nearest neighbor among a set of reference points. To achieve that, there are two basic operations, which are the Euclidean distance computing and top-case sorting. Here is an example. First, the distance is computed between each reference point and the query point. And then 3 points with minimal distance are selected if we need to find 3 neighbors. Previous studies have focused on algorithm and architecture level optimization. For example, they succeeded in optimizing the irregular memory access, reducing the search space, and improving the computer parallelism. However, they overlooked the operation level optimization, especially the distance computing and top-K operation. There are 3 observations in operation level. The first is that most computation in Euclidean distance are unnecessary. For example, there are 2 1D points which are located in 315.3 and 116.2. And after traveling several reference points, the current case minimal square distance is 16. And now we need to identify whether these reference points belong to the K nearest neighbor. A normal method is to compute the accuracy result and then compute the compare with the K's minimal distance. However, this accuracy compute may not really necessary. For human beings, we can easily confirm that this reference point did not belong to the neighbor point, even if we don't compute out the accuracy result. In fact, we even don't care about the exact value of the last 2 digits of this member because the higher bits of data have a great impact on the computation result than the lower bit. So in this work, we managed to compute the distance from the MSB to the LSB and estimate the lower bound of the distance. So when we can terminate the computation as soon as the lower bound exceeds the current case distance. In this way, we can reduce the compute and memory access cost. The second observation is that the prompt cloud exhibits various range and precision requirements across scenarios and even across dimension. The left side of the left side of the fridge shows that the 3D sensor employed in UAV car and in hand, the data range varies from 2,000 meters to 0.5 meters, while the precision requirements increase from decimeter scale to millimeter scales. Moreover, the range among the 3 dimensions differs even in a single scenarios. We have conducted a distribution of prompt coordinates in Waymond's data street. The results reveal that the range of the x and y dimension is much larger than the range of z dimension. Current accelerator often use a fixed point data type to process the point cloud, which cannot adapt to various precision requirements. To address this, we propose adaptive accuracy compute method for point cloud. The third observation highlights bit peddling causes a waste of memory. For example, the parallel N uses 3 15-bit fixed points for 3 dimensions of the point cloud. In order to align to the 64-bit size, 19 bits are used to peddling the data. The useless peddling bits will cause a waste of memory access. In this work, we present a new data layout method to remove the peddling bit. Based on the bold observation, we found that bit serial computation technique is very suitable for KN search. Let's introduce the bit series compute first. The bit serial technique, which is BSC, is a computation method that selects mapped bit data into mapped 1-bit data and process 1 bit per cycle. Recently, BSC has demonstrated success in accelerating KNs, which K operation is inner product. However, the square Euclidean distance is different with inner product operation. This BSC technology cannot be directly applied in accelerating KN search. So in this work, we employ the series and architecture for bit theory computation to KN search. We propose a series of mechanisms and architecture include bit theory computation method, early termination mechanism, data encoding methods, and layout method, as well as the hardware architecture. This new method enables the accelerator to reduce unnecessary computing and memory access and adapt to various data processing requirements. Firstly, we introduced the bit series computing of Euclidean distance by introducing some metrics and a series of driven square Euclidean distance can be calculated in a recursively. The detail of this part is shown in our paper. We can see the distance can be called bit by bit and with the sum of 3 simple components. Then we estimate the lower bound of the distance during the computation. This part is, you can find this part in our paper again. With the aid of this low bound estimate method, the computation is terminated when the lower bound exceeds the case nearest point distance. Here is an example to show the effort of the early termination mechanism. Assume that the current case minimal square distance is 100. The normal bit theory computation, in normal bit theory computation, the distance between 2 points require 8 cycles. The result is 466. However, if you estimate the low bound every cycle and estimate value is shown, the estimate value is shown in the read point, the computation can be terminated at 3 cycles as the lower bound is larger than the current K nearest neighbor. Secondly, to support the bit theory computation, we also design a encoding method and data layout. The encoding method serializes the point coordinates into a bit flow. It first removes the unused bit and then serializes the data into from the MSB to the LSB and alternates among 3 dimensions, which can match the order of the bit theory distance computation. The next thing is how to store the variable length of bit flow into a fixed width SRAM without peddling bit. To address this issue, we propose a new bitwise layout. The cartoon shows the example of a grid 8 bit flow into a 8-width SRAM. After that, we design a bit theory architecture for KN search. The accelerator includes 2D mesh of the bit theory distance units, top K units, and serial buffer. This page shows the detailed structure of the bit theory distance units. It consists 3 components, which are the square distance logic, lower bound logic, and issue logic. Our work can be easily combined with existing KN accelerator. To achieve that, some serializer should be added to encode the bit point cloud into a bit flow, and then replace the bit pile level distance units with the BDU array. We use 2 baselines to evaluate our design. The first is a linear architecture to perform the actual search, and the second is a parallel NN architecture, which is an approximate search baseline. For far computation, we also developed 2 bit theory accelerator, which is BitNN and bit theory parallel NN, corresponding to the linear and the parallel NN architecture in baseline to evaluate the bit theory technique. We use 4 point cloud data sets. This data set covers a range of indoor and outdoor scenes with varying point cloud size. Performance evaluation shows that the BitNN accelerator achieved a speed up of 5.5 times for the exact search compared to the linear architecture. The bit theory parallel achieve a speed of 3.4 compared to the baseline architecture. Benefit by the point cloud encoding method and the early termination mechanism, BitNN accelerator achieve a reduction of 17% in SRAM access and 15% in DRAM access. We further analyze the reason. This page shows the histogram of the percent of computation cycles for 4 workloads. The encoding length of these 4 data sets are from 38 bits to 49 bits. With the aid of the early termination mechanism, the average computation cycle are about 9.7 cycles to 17.4 cycles. We also found that less than 2% of points need the full computation, reveals that the importance of the early termination mechanism. More detailed evaluation are provided in the paper. This analysis offers a deep understanding of the BitNN accelerator's performance under different conditions. In summary, we found that most computation in KN search are unnecessary. Based on this observation, we propose a Bit-Serial accelerator for KN search. The serial optimization method results in significant improvement in performance, power efficiency, and memory access. Thank you for your time. Does anyone have any question?
Any questions from the audience? So while we are waiting for questions, I had a question for you. So as it comes to the early termination, can you comment on how the number of neighbors to search would have if it would have any impact on the early termination?
When the number of the neighbor is large, the threshold of the early termination will large, and they will decrease the performance. In our evaluation, we found that the performance dropped within 5%.
Great, thanks. If there are no more questions, let's thank the speaker again. And next we have Dr. Feng again presenting another paper. So whenever you set up, please.
Hello again. My name is Feng. In this talk, I'm going to talk about Cicero, which is a algorithm and architecture co-design for neural rendering. So this is a joint work with University of Rochester. So as humans, we love visual pleasant scenes like photorealistic renderings in movies, VR games. I assure that people love Finding Dories. And while photorealistic renderings can provide unprecedented visual qualities, conventional ray tracing pipeline inevitably require complex geometry modelings, texture descriptions, etc. Put in one sentence, traditional ray tracing pipeline is super complex and slow. On the other hand, neural radius field, also called NeRF, is a faster alternative to conventional ray tracing pipeline. And NeRF leverages the conventional image-based rendering and approximate the entire complex object image interaction as a radius field. Specifically, the way that NeRF generates a pixel goes like this. So it first casts a ray into a 3D scene. And then it samples along the array to get a set of sample points. And the pixel value of this array is determined by accumulating the radius of these sample points. For each point, it will find the corresponding intersect voxel in the feature embeddings, which actually represent the 3D scene. Once the sample point finds its voxel, each sample point will find the 8 vertices of that voxel and gather the features of these 8 vertices. And then the sample point will compute its feature by trilinear interpolating the feature vector of these 8 vertices. Finally, each sample point passes the intermediate feature through a lightweight MLP model to obtain the actual density and the radius value of that sample. So as you can see, the computation of each pixel is independent. Despite NeRF accelerating the rendering pipeline significantly, it still cannot achieve real-time performance on today's commodity mobile SoC. Here we show the performance of different state-of-art NeRF algorithms on NVIDIA mobile SoC. As we can see, none of them can achieve real-time performance 60 frames per second. And from the results, we can draw 2 conclusions. First, today's NeRF algorithm cannot achieve real-time performance on mobile devices. And today's model size far exceeds the on-chip SRAM sizes, leading to frequent memory traffic. Therefore, we propose Cicero, an algorithm and hardware co-design for NeRF. Specifically, we propose a sparse radius swapping algorithm to reduce the total computation, and we also propose a memory-centric rendering pipeline to reduce the overall memory traffic. Now, let me first talk about the intuition behind our algorithm. So assume that we have a camera at position T0. It captures the object surface. And on this object surface, we have a physical point at P0. It captured by pixel P1. Now, if this camera moves from position T0 to T1, and also render a frame, and this field of view also captured P0. If the camera movement is small enough, we can actually reuse the pixel from P1 from the previous render frame to the current frame at P1 prime. And we call this technique radius swapping. In our experiment, we show that the overlap pixels is over 98% across the frame during real-time rendering. However, there's one caveat here, which is that we require depth of each pixel in order to perform this radius swapping. And, well, in AR/VR application, it is easy because the depth map can be easily obtained from projecting meshes. Using this insight, now let me introduce our algorithm. Our algorithm, we first warp the reference frame from the reference location to the current location. And however, simply doing that will introduce these occlusions. So these occlusions happens when the previous occluded scenes become visible in the current frame. To address this issue, we simply perform NeRF rendering for those missing pixels. Because remember, each pixel rendering is independent in NeRF. And by doing that, there's no these occlusions. And in our experiment, we show that by computing those missing pixels, we only roughly need to compute 12% of pixels. Here, let me show the accuracy comparison. In addition to the baseline, we also compare against another baseline, which is downsample by 2. So this baseline first downsample the frame by 2 and render for NeRF rendering, and then upsample it to original resolution by bilinear interpolation. Now let's see the result. As we can see, Cicero outperforms downsample by 2, and it just degraded accuracy compared to a little bit compared to the baseline. So that's our algorithm. So using our algorithm, we can reduce the computation for those warped frames. However, we still have to perform full-size resolution for those reference frame, right? So we are going to introduce our memory-centric rendering pipeline in order to address the memory traffic. So the original rendering pipeline is pixel-centric, in a sense that every pixel will need to find the intersect voxels for each sample point, and then gather the features from the memory, sometimes from DRAM, and to compute this pixel. In this example, we have to gather V1, V4, and V7. And after we compute this pixel, we're going to compute the next pixel. And in this case, we need to gather V1, V5, and V8. Now imagine if the on-chip buffer is small enough. For instance, we can only store 2 or 3 voxels. And in that case, as we can see, the DRAM access becomes irregular and non-streaming. This might also introduce redundant memory access. To address this issue, we propose a memory-centric rendering pipeline. In our pipeline, we first split the entire feature representation into blocks, and each block contains multiple feature voxels. Then we first perform all the ray voxel intersections and collect the results into a dictionary. So the key are the block IDs, and the values are the ray sample IDs. And after we're doing that, we are going to compute the radius value for those samples block by block. And in our algorithm, we assume that the basic hardware setup looks like this. So we have a DRAM which stores all the voxel features, and we guarantee that the voxel features within one block are stored in a continuous memory. And then we have a double buffer that can store at least one block of feature voxels. And then we have an array of compute units to perform MLP operations. And during the computation, each time we load one block into the working buffer, and we iterate all the sample points to compute the radius value. And meanwhile, we are going to load second buffer into the filling buffer so that we can overlap compute and data fetching. As we can see, by doing so, every feature blocks are only required to be loaded once, and all the DRAM access becomes streaming. In addition to our memory-centric rendering pipeline, we also augment existing hardware to accelerate the rendering process. In our hardware, we have a DRAM to store neural representations and also MLP weights. And we use a GPU to perform indexing, and we use NPU to perform gathering and feature computation. And in our NPU, we have a Cicero array to perform feature computation, and we have a global buffer to store voxel features and rendering results. In addition to that, we also augment our gathering unit on this NPU. So it can accelerate the gathering operation and also eliminates the SRAM bank conflicts. Due to time limit, I will omit the detail here. Please refer to our papers for more details. Overall, the hardware augmentation merely introduced 2.5% of area overhead compared to the baseline NPU, and which shows that we can achieve significant speed up. Now let's see our results. So in our experiment, we implement a 24 by 24 Cicero array with 1.5 megabytes on-chip buffer, and we also augment the gathering unit to the NPU. And we evaluate 3 NeRF models, and in our evaluation, we have 3 variants. The first variance only applies a spiral algorithm, sparse radius warping algorithm, and the second variance applies both spiral algorithm and memory-centric rendering, and last one is our full-fledged version including hardware augmentation. Now let's see the results. So in our evaluation, all the values are normalized to our baseline, which is we render the full-size NeRF full-size image through NeRF rendering, and our hardware design and use based on our execute our hardware design without the gathering unit. Now let's see the results. So the x-axis shows different networks, and y-axis shows speed up. And as you can see, by applying spiral, we can achieve 8 times speed up, and applying spiral plus memory-centric rendering, we can achieve 9 times speed up. And combining all of that, our Cicero can achieve 24 times speed up. On the energy saving side, we also show that our Cicero can achieve significant energy reductions. In this case, we can achieve 20 times speed up, 20 times energy reduction. So in conclusion, Cicero fuses conventional image-based rendering with NeRF to reduce up to 95% of MLP computation, and Cicero transform a ray-centric rendering to a memory-centric rendering, achieving an order of magnitude speed up and energy saving. And that would be end of my talk, and I'm happy to answer any questions. Thank you.
Questions?
Huiyangzhou, NC State. Yeah, very nice talk. Also very interesting ideas. So I got a question about your approach using those warped, kind of frames. So my question is about, how often will you need to generate the reference frame? Because you cannot always use these warped ones, right?
Right. So in our paper, we actually have a very nice idea which can overlap reference rendering with the warped frame. Because we can imagine users are using VR devices and the trajectory is very predictable. So you can basically predict some reference locations, and you can pre-actively render these reference locations. And for instance, if the current frame is very close to the reference frame, you can do the warping. Otherwise, you can just do the full frame rendering. And in that case, there's energy overhead, but there's no latency overhead. Yes.
Okay, thank you.
Yeah, thank you.
All right, if there is no more question, let's thank our speaker again.
Number 5. Give me one second.
All right, so our next speaker doesn't really need an introduction, Dr. Mahmoud Kandemir, because he is a member of Hall of Fame of ISCA, Micro, HPCA, and actually an IEEE fellow. But again, I can just briefly introduce him that Dr. Kandemir is a professor in the, should I continue?
Yes.
Okay. In the Computer Science and Engineering Department at the Penn State University. He is a member of Microsystems Design Lab. Dr. Kandemir is the author of more than 150 journal publications, over 60 and 650 conference papers. He has graduated more than 32 PhD students and 20 master's students, and his research has been funded by several agencies, including NSF, DOE, DARPA, SRC, Intel, Microsoft, and many more. He is a recipient of NSF Career Award and the Penn State Primary Research Award. So, yeah, please go ahead. Thank you.
Thank you, Bahar, for the long and nice introduction. Hi, everybody. This is the work that mainly done by two of actually our students in our group, Sandeep Buhuyan and Ziyu Ying. It would be best if one of them was here to present it, but both of them graduated and they just started their new career and couldn't leave the country. And because of that, I have to present it. And in preparing for presentation, actually, I realized one thing. That's not the first time that I'm presenting on behalf of my students, but those were the papers actually about compilers, computer architecture, and etc., which I had hands-on experience. But this is about the games, for which I didn't have any experience, so it was actually kind of difficult for me to prepare as well. Anyway, let's start. So the idea is that mobile games and the contribution of mobile games into overall game world keeps increasing. And based on the 2022 statistics, basically more than 50% of the games are some sort of mobile games in terms of the revenue share. And so there are several reasons for that, but two of the important reasons is that a growing increase of smartphones. And the second thing is that the convenience actually that the games are given to smartphone users. You can play it anywhere, right, anytime you want. And the problem with the mobile games is that, though, the quality is not as good as the games actually that you would, play, the same game that you would play actually on a PC. And here on the left-hand side, you see actually a scene from a mobile game, and the one on the right-hand side actually on a PC game. And you can see actually that in the PC game, we have much more details compared to the mobile version. right? And this is a big problem. This is a big problem, and there are obviously several reasons for that. And one of them is the limited processing power of the mobile hardware. So you need to basically skip some details or approximate them. And secondly, battery is an issue, and you need to adapt to that as well. And third thing is that mobile market, unlike the PC market, is really huge. Variations across the architectures in terms of both software and hardware are huge. So it's kind of difficult to optimize the same game on multiple platforms with equal strength. So what is the solution? So the one actually popular and now widespread solution is what we call actually the cloud gaming. Now cloud gaming is very interesting because what happens is that the compute-heavy tasks of the game are really actually offloaded to cloud, and you use your device, whether it is a cell phone or whether it is a AR/VR device, as a kind of just an interface, right? And with the boost from the cloud, now we see actually that the number of mobile game users increased significantly, and in 2022 we got 2.68 billion mobile game users versus slightly over 1 billion PC gamers. And you can see that actually a large fraction of the world is playing mobile games. And unfortunately, there are two important challenges here still. One of them is bandwidth, and the other one is latency. So from the bandwidth angle, you have to basically get your frames from the cloud, and that basically increases latency. And from the latency, that basically affects the performance. And from the latency perspective, you need to be careful because for high-end games, in particular 3D games, the actual frames should be rendered at a certain rate. Otherwise, your visual experience as well as the overall game experience would suffer. So then what is the solution? Now, before actually going to that, let's look at actually the pipeline. And some of you are familiar actually with this type of pipeline because it's very similar to the video pipeline. And here we got the game engine, and then basically game engine is where the logic of the game takes place, and you decide the next move and whatever, depending on the type of the game. And then you generate frame and render it, and you finally compress and encode it and send it. And on the client side, and in this work we focus on a kind of a smartphone type of architecture, and you decode the frame and display. So that's the idea. Now this is, as I said, kind of similar actually to the video streaming pipeline, but not exactly the same. Because in video streaming pipeline, what happens is that instead of from the game engine, you got the video input. And video input actually videos, streams, or the frames can be actually encoded offline, can be downloaded in bulk, and etc. So there are certain advantages of them, whereas compared to the games, everything is happening in real time, and it's very interactive. And the gamer's behavior affects all the things basically that are happening. Okay, so now one of the, clearly, let's say that if you want to render the image in the cloud using actually 1440p pixel resolution, then what's going to happen is that you are going to spend a lot of time in rendering it on the cloud, and as well as encoding and sending it. So there's going to be both compute and latency components, right? And then you have to decode it. On the other hand, one idea actually that has recently been done, saying that, okay, why don't we do, maybe in the context of the games, use actually lower resolution and render it using lower resolution and transfer it to the client, and the client somehow actually boosts the resolution. So that is called super resolution. It's not particularly very new. People used super resolution, I don't know, maybe a while back, but what they were using actually simple bilinear interpolation type of algorithms. And these are the algorithms that are doing interpolation on basically two variable functions, right? Now recently, as you can imagine, people started to use neural networks for this, for doing this resolution. And here, for example, I can actually generate and render the image in 720 and transfer it. And then I can do actually super resolution, and it's going to be 1440. So, and I can reduce network bandwidth significantly actually in doing so. Now, so this is a good solution in general, but the problem is that this neural network itself is very heavy. And there are actually networks designed specifically doing this type of task, but still they are very heavy, even if you are using accelerators, right? And because of that, you may not be able to meet the real-time constraint. For example, EDSR is one of the most popular ones, and if you use it, actually, you are going to get slightly over 4 frames per second, which is much lower than you would desire actually in a high-end mobile game, 60 frames per second. So we need to find actually another technique, although super resolution is good, but it will not work perfectly actually in the context of mobile gaming. Now, what is that? So, or what did people do actually to address that? So one of the things actually is that, okay, since this is a neural network and there are so many actually neural network pruning works, maybe we can prune it, right? And you can do that, and there are lots of works actually already published doing that, but still actually there's a limit to that. And in most cases actually, depending on the game, you are unable to achieve what you want. So one interesting work actually coming from 2020 is called NEMO, and that was a very influential work, an excellent paper. I encourage everybody actually to read it. And the idea was that actually, instead of using super resolution each and every frame, we can use it actually only for reference frame. And then what we can do, we can actually cache the results and reuse them actually to reconstruct the non-reference frame. So that was the idea. It was requiring some changes actually to the codec architecture, but it was generating actually very good results. So which inspired actually our own work. And that is developed in the context of, again, video streaming. And when we come to the game programs, though, this applying super resolution to the entire frame, reference frame, can be very costly. And here I'm showing actually a simple example. X-axis is the frame index, y-axis is the upscale in latency. And you can see actually in the reference frames, there's a huge bump, which is actually problematic, right, for games. Now, so what do we want to do? Now, at this point, we want to stop and ask this question, what do we need? Well, we need real-time latency. This is one constraint. And second one, we don't want to compromise quality too much. So these are two conflicting, right, constraints. That's what we want to do. And now let's see actually what are the different upscaling factors, right? What are their effect? So if you look at here, for example, in this graph, what I'm showing here in the first one, what I'm targeting actually 1440. That's the maximum right now that I'm working on. And suppose that on the in the server, I use actually 720. And then I upscaled it. And suppose that instead of 720, I use actually 480. And then upscaled it and so on. Now you can see that on the first left side y-axis, as I use actually lower resolution, right? And it's going to take less time basically, right? But on the other hand, the quality is also going to suffer. So if I want to go for quality, for this particular example, maybe actually I would go actually with an upscale factor of 2, which means use 720. But if you use 720, then it's basically the latency is going to be too much, right? From the quality perspective, it might be fine, but from the latency angle, it is not fine. And if you work with, let's say, 360, it is the other way around, right? From the latency angle, it would be good, but from the quality angle, it would not be good. So then what should we do? And there actually comes to an important feature of the game programs. Game programs are really actually driven by the user behavior, gamer behavior, and gamer attention. Not all the parts of the frame actually take the same attention. Typically, one or two objects of interest, depending on the game, and they are more important, right? Then actually what we do, we define the concept of region of interest. Then we ask ourselves this question, whether it is possible just for region of interest actually use higher resolution, and for the remaining ones actually parts use then actually lower resolution. So that is the main idea. And so in other words, we are going to upscale the smaller but important frame region. For each frame, we are going to do that using actually DNN-based super resolution. And the remaining ones, actually, we can use lightweight traditional upscaling techniques. And our implementation is quite modular. For both the region of importance and the other regions, you can use actually anything, any algorithm that you want, as long as one of them actually is more costly and more accurate, and the other one is less costly and less accurate. And, okay, now the question is that obviously how are we going to get this region of interest information? So I'm not going to go into the too much details. In the paper, actually, there's a section that describes how we should select the region of interest, what should be the size, and so on. So, but to summarize here in this slide, we used actually what is called depth data. So the depth data is a kind of a data actually that is stored in a depth buffer and indicates actually whether the object is closer to the viewer. For example, in this particular scenario, you can see the guy actually it is dark, so because it is closer to our viewpoint. And as you go actually further, so it becomes lighter. So this is the depth information. And in the paper, there are different ways of obtaining region of interest from depth information. A couple of ideas actually are laid out in the paper. But the main thing is that, right? Main thing is that while actually you are doing this server-side frame processing, there is a pixel shading part. And if you look at actually, if you focus on this frame rendering part, this pixel shading part actually is, you identify whether actually shading is required and what kind of shading and so on. There actually, at that point, depth information is available. So you don't have to do much extra for that. Now the idea is that then, can we actually, render the image in low resolution? And with that image, can we pass the actually, using this depth information, can we identify the region of interest and pass it actually to the client side, to the mobile device? Okay, so our framework then has two main parts. Some of the things that are going to be done on the cloud side and some of the things that are going to be done on the mobile side. So in the cloud side, I'm not going to go into the details, but you got the game engine, then rendering and so on and so forth. But at the end of which, you basically have compressed frame in lower resolution, and as well as the region of interest coordinates in the frame. And you transmit them actually over the network. Then in the mobile part actually, you do frame upscaling and region of interest upscaling actually, and then using a different technique, as I mentioned, and non-region of interest regions using a different technique. Now, if you got limited, and you are going to have limited resources obviously on the client side as well, how to utilize those resources to do actually these two things in parallel, itself an interesting research question. In the paper, we mentioned a couple of ideas, but those are kind of a very high level. The more work actually is needed along that direction. Okay. Now, I hope I was able to give you the kind of a high-level idea. Now, I would like to briefly talk about the results. We extensively evaluated our idea, comparing it actually with state-of-the-art, which is NEMO that I mentioned, and we evaluated it from multiple perspectives. So one actual perspective is, okay, per frame processing, right? How much actually we were able to achieve, how much savings we were able to achieve over state-of-the-art. And second thing is the end-to-end latency, okay? And third thing is that the energy consumption, and fourth is the impact on quality. And in all these metrics, actually, our approach fares better. Now, this is showing the speed up, actually, for reference frames and non-reference frames and averaged over GOP. It's a group of pictures, one reference, and in this case, 59 actual non-reference frames. And you can see actually that for, as expected for reference frames, we achieve significant benefits. But even when you consider actually all parts of the all frames in a group of pictures. On average, actually, we have 2x speed up. But again, this is not the complete picture. Obviously, you have to look at actually the end-to-end latency. And this end-to-end latency actually, when you look at end-to-end latency, so since cloud games are proprietary, obviously, we focused on actually, instead of cloud, we mimicked it actually using a powerful desktop with NVIDIA GPU. And for client, actually, we made experiments with 2 different smartphones. And now one of them is Google Pixel and the other one is Samsung. And as we can see, actually, we achieve significant benefits from the end-to-end latency perspective in both the cases. And finally, I would like to talk about the energy. And again, compared to the state of the art, our approach brings significant energy because in general, we don't do actually super resolution on the entire frame. And instead we do it actually on a smaller portion of it. And so there is energy consumption is higher actually on or energy savings are lower actually on S8, mainly because their actually display consumes much more energy compared to the other architecture that we used. So, and more results and detailed descriptions of the algorithms that we use can be found in the paper. So to summarize, now our approach enables high fidelity game streaming on commodity mobile platforms. And we do actually super resolution, but we do it actually in a kind of a more selective fashion. That is the main idea. And as to identify the region of interest, for which we used to use actually DNN-based super resolution, we exploit the depth information that is available. I'm saying that it was available, but it's not very, very available, to say the least. So we had some effort actually to get that. In fact, one of the maybe architectural insights on that actually to make this depth information more easily available for this type of optimizations. Finally, our results showed that actually I didn't show the improvements in the quality as well, but there's slight improvement over state of the art as well, but that was not the main purpose. We have significant benefits in both performance and energy. So that is all I want to say. Thank you.
Hi, I am Taehyun Baek from Samsung SDS in Seoul. I have a question that what is the games that you were benchmarked for these results?
Yeah, so the description of the games are in the paper, but basically these are mostly 3D games.
What I want to know is that what the games you were benchmarked is the first-person view or third-person view or quarter view things?
No,
because
it is only first-person and third-person view.
Okay, so yeah. I think because what I have a question about is this approach would be effective on the first-person or third-person view, but the depth information would not be effective on a quarter view games like Diablo 4 or a lot of things because I'm also a hardcore gamer. So I had the question.
No, I completely agree. I should have said that. That is correct. That is not for all the games. And especially if you don't have the full vision, that is not. And also some games, even if you have the full vision, they don't use depth information, like, for example, chess and etc., because every component is equal, in a sense, importance. So those things, it is not applicable.
Thank you very much.
Thanks.
Trent from ByteDance. My question is really on the, let's say if you can not only doing that for games, but also for videos, then does that mean you can add that information, then you can have the technology applicable to video streaming?
So my understanding is that because these things are proprietary, not all the games have depth information. So that is basically, if you want to optimize them, first of all, you have to kind of obtain that information and generate that information and then use it. And we didn't look at that. It is probably doable, but I don't know what the benefits would be.
Hi, I'm underground from Brazil. What do you think would be the impact of using like this algorithm in a network for more latency and higher loss of packets?
Yeah, so actually with even 5G experiments that we made, we have a lot of lost packets in general. In the default case, since our approach reduces the dependence on the network a bit, so it is we are doing better. But I think the issue that you mentioned is a very big issue. And since overall, actually, we reduced the number of total packets, so we are doing better. But we are not doing anything specific on that. So one extension really would be actually to look at this under different network conditions. That would be, in my opinion, a very good study, performance study.
Awesome. Let's thank the speaker again. And that concludes this session and this fantastic ISCA as well. I guess I can see you next year, but it seems that the PC chair himself is here.
Thanks, Bahar. Yes, that ends ISCA this year. I think the other session is running 10 minutes late, so if you want some more technical content, you can head there. But otherwise, we are done. And please take a moment to thank the general chairs. I think they've done an outstanding job, kept us well fed and well entertained. So do convey your thanks to them as well. And otherwise, yeah, we'll see you in Tokyo next year. Thanks.